Welcome to Learning Math with Mr. Tan. Today I'll be talking about a slightly more advanced concept called modular arithmetic, and this is used in cryptography, and for students who are taking Math Olympiad, this will be a very useful concept for you to break down very large numbers and to analyze it further. So what is this modular arithmetic about? So you have at the top this statement which reads A congruent B mod n. So essentially, this I would of course explain this a little further. This means to say the number A is congruent to a number B, modulus n. Alright, to understand this, this means both A and B gives the same remainder when you divide it by a divisor n. So of course that's a very abstract, alright? So let's use actual numbers to help us understand this a little bit before we talk further. Alright, so we have, for example, the number 5 and 3 as you see below, right here. And if I were to consider division algorithm where I divide both numbers by the same divisor of 2, alright, we're going to get quotient of 2 for if I divide 5 by 2, and I'm going to get a quotient of 1 if I divide 3 by 2, alright. But more importantly, let me just get rid of all these arrows. More importantly, both of them gives me the same remainder 1. So there is going to be a same remainder of 1 where I divide both 5 and 3 by 2. Alright, so essentially by what we defined earlier on, we can say that 5 is congruent to 3 in mod 2. Alright, so we're going to study this a little bit further. So just do take note that this 3 over here, the number on the right here, is, we shouldn't really see it as a remainder when you divide 5 by the divisor 2. Alright, so it's just that both these two numbers, 5 and 3, has the same remainder, alright, of 1 when you divide it by 2. Okay, so next we will look at this. So a little bit further, so not just mod 2, we could also have mod 3, blah blah blah, mod 7, and so on. So this is very useful for when there are cycles of numbers. So for example, 7 days, all right, we will be looking at the world of modulus 7. And if we're looking at even numbers, then we will be looking at modulus 2, for example. So let's talk about modulus 2 first. Right, modulus 2 gives us two possible numbers on the right of the congruent symbol. So basically, for example, I could have a 2 is congruent to 0 modulus 2. I could have a 3 congruent to 1 modulus 2. But of course, if I go up to 4, then it goes back to 0, where 4 and 0 have the same remainder and modulus 2. Alright, so this is what it's about, and this gives us a very cyclical kind of thing. So let me just erase this. Alright, so these are the two possible numbers, 0 and 1. So the same way, and if you realize that for the two acceptable numbers, right, the larger number is always going to be 1 less than the modulus. Alright, so for example, in the world of modulus 3, we're going to have 0, 1, 2. Alright, so take for example, if you analyze the number 3, it's going to be congruent to 0 mod 3. Alright, so because both 3 and 0 is going to give you the same remainder of 0 when you divide by 3. Alright, so 4 is congruent to 1 mod 3, 5 congruent to 2 mod 3, and then when you get up to 6, the same thing is going to happen. It goes back to 0 because both 6 and 0 gives you a same remainder when you divide by 3. Of course, you could still raise it as, you can raise it further and say, okay, 6 is congruent to 3, following from 5 congruent to 2, mod 3, but that would be, you know, unnecessary, for lack of better word. So I'll say, since 6 is congruent to 3 mod 3, and then 3 is also congruent to 0 mod 3, and then you realize that, hey, look, it's going to go back to 6 congruent to 0 mod 3 anyway. And that's it. So that for modulus 3, the world of modulus 3, you're going to get 0, 1, 2. Alright, so again, same thing, the largest number here, 2, alright, is 1 less than the 3 itself. Okay, so I'm going to erase all these. Okay, and likewise, in the world of mod 7, you're going to get 0, 1, 2, 3, 4, 5, 6, and then it goes back to 0 again. Alright, so I'm going to take a number line to further help you understand this as a sort of a mapping of numbers. Again, not very, can't think of a better way to put that. So in the world of mod 4, we're going to have 0, 1, 2, 3. Alright, so for example, 4 will be congruent to 0 mod 4, alright, and 5 will be congruent to 1 mod 4, for example. So let's start from 0. Alright, so when I divide 0 by 4, I'm naturally going to get 0. Alright, so when I divide 0 by 4, right, I'm going to get the same remainder as 0 when divided by 4. Of course, that's stating the obvious. Alright, but of course, let's go on to the next number. When I divide, like for example, a more meaningful one would be if I were to divide 5 by 4, right, I'm going to get a remainder of 1. Okay, which likewise, if I divide 1 by 4, right, I'm also going to get a remainder of 1. Right, so from 0, the next number being 1, then 2, when I divide by 4, I'm going to get a remainder of 2. Right, 3 divided by 4, remainder 3. And 4 divided by 4, of course, the remainder is 0. And then this cycle repeats itself. And then we have 9, when divided by 4, goes back to, so when you divide 9 by 4, this cycle goes back to 1. Alright, so we can also do this for negative numbers. So if you observe this pattern, so to speak, right, so this is going to go to 3, goes to 2, goes to 1, goes to 0, and then of course this goes back to 3 again. So I just want this sort of mapping here for you to see that, okay, it's quite a cyclical thing. Alright, so we can also say, for example, negative 3 is congruent to 1 mod 4. Of course, in a later video, I'll be talking about how to, convince ourselves, so to speak, right, to say that, okay, negative 3 congruent to 1 mod 4 doesn't seem very intuitive, but there is a way to sort of verify this. Alright, so thank you for watching this video, and I hope this gives you a little bit of idea how this modulus arithmetic works. Until then, goodbye.